It's a pleasure and it is an honour. I'm incredibly proud to be able to welcome you all today here in the lecture theatre, also those of you who are watching online, to the inaugural lecture for Professor Grigory Garkusha. Inaugural lectures are a great opportunity for us to come together to celebrate an important professional milestone with colleagues, with family, with friends, and also it's one of the things that makes me so proud. It's an opportunity for us to showcase some of the excellent world-leading research, excellent teaching, our innovation and our enterprise and engagement. Grigory is a professor in the Department of Mathematics here at Swansea University. He completed his PhD in mathematics at St. Petersburg State University. I don't have any dates on here.
1999.
No, and I wasn't...
28th of April, 1999.
Oh, well done. Okay.
Yeah.
Just after tea time.
After 4 p.m., I think.
Okay.
Yeah.
Okay. Before becoming a research fellow at Manchester University. Later, he followed a postdoc position in mathematics at the International Centre for Theoretical Physics in Italy, before he returned to Manchester University as a research fellow in 2006. And then he joined Swansea University as a lecturer in 2007. Grigory's received invitations as a research visitor for the Institute of Advanced Scientific Studies in Paris, the Mittag-Leffler Mathematics Institute in Stockholm, and the Centre for Advanced Study for the Norwegian Academy of Science and Letters. Grigory's research interests lie in motivic geometry and topology, K-theory, algebraic geometry, category theory, and rings and modules theory. So without further ado, I'll hand you over to Grigory and his lecture, Motives and Transfers.
Yeah, many thanks indeed for the introduction.
It's a pleasure.
And many thanks everyone for staying here late afternoon. And I would tell about motives and transfers. This front page is from my 2012 EPSRC grant, consists of some buzzwords where you can see several names and some mathematical words, which I'll try to explain within next 40 minutes. I would start with the introduction into the topic, and first of all, I would mention a key figure in mathematics, Alexander Grothendieck, who actually designed many areas of modern mathematics. And my research, directly or indirectly, everything, in fact, goes to ideas and results of Alexander Grothendieck. He, by many people, he is regarded as the greatest mathematician of the 20th century. But if you ask me, he is the greatest mathematician of all times. And it is amazing that he was active in mathematics only within 15 or 16 years. He was between mid-50s and early 70s. And within these years, he revolutionized several areas of mathematics. In particular, he was the leading figure in modern algebraic geometry, homological algebra, category theory. He also discovered K-theory, and he unified several branches of mathematics, and his ingenious ideas and constructions are still influencing and continuing. In particular, Grothendieck discovered K-theory, and he envisioned the theory of motives in the 60s. And these insights led to some breakthroughs in the 90s and 2000s, and led to several constructions of motives. I should mention in the next slides two key figures of the motivic homotopy theory. Motivic homotopy theory is a relatively new topic in modern mathematics. It is a blend of algebraic geometry and algebraic topology. It was largely created by Fabien Morel from University of Munich, and Vladimir Voevodsky from the Institute of Advanced Studies. Unfortunately, he passed away recently at the age of 51. And motivic homotopy theory led to some striking applications in mathematics. For example, I should mention here the Milnor conjecture, which was solved by Voevodsky in 1996, for which he was awarded a Fields Medal in 2002 at the Congress in China. And also another striking conjecture application is solution of Bloch-Katte conjecture by two mathematicians, Rost and Voevodsky. Also, the ideas and constructions of motivic homotopy theory attract many mathematicians in related areas, especially from topology, number theory, K-theory, and the majority of people who were involved in algebraic K-theory moved over the time to motivic homotopy theory. So let me also pass to other two mathematicians. My research is also related to bivariant KK theory, and I will briefly explain how these areas can be connected, and it will be in the content of the following slides. But let me start with Gennady Kasparov, who invented the so-called KK theory of C-star algebras, an important field of functional analysis. Also, it is reminiscent of Grothendieck philosophy of motives, and KK theory also plays a key role in modern non-commutative topology in the sense of Alan Kohn, a Fields medalist, and also it is an important tool for the investigation of the Baum-Kohn conjecture, which is still open. Gennady Kasparov was originally motivated by the Novikov conjecture in geometry, and I should also mention Joachim Kunz from the University of Münster, and who provided a new look to KK theory, and he has made fundamental contributions to the area. And I must admit that technique of Joachim Kunz and his results will play a crucial role in some of my papers I will briefly mention today. Okay, and I moved to Swansea in February 2007, and this is one of my first publications published in Advances of Mathematics. This is an article dedicated to homotopy theory of usual non-commutative rings. We use rings every day. These are sets with two binary operations, addition and multiplication. For example, we use them to avoid mistakes interchange when shopping, for example. And also, we start our MA111 module with rings. And in fact, the constructions about algebraic counterpart of KK theory will be explicit, and a student having our module MA111 Foundations in Algebra should be able to understand basic definitions and constructions of algebraic counterpart of Kasparov K-theory. So this paper is dedicated to homotopy theory for algebras or for rings, but what is homotopy theory? Homotopy theory is part of modern geometry and topology, and it investigates geometric objects up to homotopy, up to deformation. We can squeeze or stretching objects and we don't distinguish them, we can also continuously transform one object to another, continuously deform it, and such kind of deformations in topology are what I will call transfers in this presentation, but I will mention algebraic counterparts of such transformations. And in homotopy theory, for example, we don't distinguish the closed unit interval and the point. So at first glance, rings and homotopy theory have nothing to do, but it is not the case. And following ideas of Morel and Voevodsky, we are able to develop more or less the same theory of motivic homotopy theory for arbitrary rings. And most difficult computation here is I was motivated by ideas and work Joachim Kunz as well as by Kartinas and Tob on the universal bivariant K-theory. And the question is whether we can apply, is there any relation between Kasparov-Kunz and Morel-Voevodsky's motivic topology, and in particular to which extent the universal bivariants KK theory are of motivic nature. But in place of algebraic varieties in the classical motivic homotopy theory, what about if we start with arbitrary rings instead? They're non-commutative, non-unital, just associative and associative rings without identities in general. So in this article, I introduce homotopy theory of rings. I introduce the notion, in particular, most importantly, what a weak equivalence is, what associated universal categories of rings, and also this leads to the following publication published in 2014, but as a preprint it's been in the archive since 2010. The next step is to associate the so-called stable homotopy theory for algebras. In topology, in classical topology, we deal with unstable topology and stable topology. What is stable topology here, where the major objects, major players here are arbitrary rings? Well, we construct a spectrum, we associate to any two algebras A and B a spectrum that represents the universal bivariant KK theory of Kunz-Kartinas-Tom. And also, what is important in this construction, it is entirely based on the Joachim Kunz approach to the classical Kasparov K theory. And this spectrum only uses morphisms between rings. So rings and ring homomorphisms, nothing else in the definition of this spectrum. This is why I mentioned that as students with our MA 111 module as a prerequisite should be able to understand the definition of this spectrum. But what does it compute? We have defined something. What are applications of such spectra and homotopy theory of rings? Well, first of all, I should mention the classical algebraic K theory, and a key figure here is Daniel Quillen, who defined high K theory of rings, and Daniel Quillen was awarded a Fields Medal in 1978. Also, I should mention that Quillen associates to a ring a topological space. A revolutionary idea was by Quillen was to associate homotopy types to entirely algebraic objects. In particular, he associates a topological space denoted by K of R, and its homotopy groups are by definition what we now call higher K-theory groups. The definition of this, there are several definitions of this topological space, but it is highly inaccessible, and it turns out that we'll be able to give another model for higher algebraic K-theory, and that uses explicit spectra, but I'll mention this later. I should also mention a book by Quillen, Homotopical Algebra, published in 1967. And let me quote here Graham Siegel, who writes that this book is the art of assigning homotopy types, or initially homology groups, to many algebraic and combinatorial structures, such as groups and algebras, which at first sight have nothing to do, have nothing space-like about them. And I should, as I have mentioned, at first glance, rings and topological spaces have little to do to each other, but it is not the case. It turns out that we can use ideas from topology to investigate genuinely algebraic objects. And this book is also important in the creation of motivic homotopy theory, or by Morel and Voevodsky. Namely, this book covers what we now call the theory of model categories. So this is very influential book, and let me pass to the next slide that asserts that our constructions based on explicit ring homomorphisms entirely recover Quillen's K-theory space. If I take R to be any regular ring refers to, it is a kind of smoothness for topological manifolds. There are plenty of regular rings, they are quite reasonable. And given a regular ring, then Quillen's K-theory as a topological space is recovered from the bivariant algebraic KK theory in our sense. If I take a couple Z and R, there's a mistake, R and Z, other way around, ZR. And Quillen's K-theory groups in particular are recovered from our spectra. And again, the spectra here only use rings and homomorphisms, something very basic in algebra, which every student in math department studies in algebra modules. Yeah, and as I have mentioned, the construction of this spectrum only requires rings and homomorphisms, and MA111 module would be enough as a prerequisite to understand its construction. Another application is that the spectra KK A of B altogether give us abelian groups defined as the right-hand sides. So to any couple of A and B, we associate an abelian group here. And it turns out that such abelian groups together with all rings recover the universal bivariant theory here in the sense of Kunz, Konstantinos, and Thom. So this universal theory is entirely recovered from spectra, which I call algebraic Kasparov K-theory spectra. And another application of algebraic Kasparov K-theory says that such spectra here, or let me pass to another slides, the spectra K A of B are also have transfers transfers in each variable a and b. And transfers are some exotic homomorphisms between rings. It is not enough to have naive homomorphism between rings. We should add plenty of further transfers or morphisms between A and B, and this is what typically happens in motivic homotopy theory or in Kasparov K-theory, in bivariant K-theory. And we enrich rings by further morphisms, which at first glance can look quite exotic. So this category defines in these terms by these groups recovers the universal KK theory of Kunz, Cortinas, and Thom as another application of algebraic Kasparov K-theory and homotopy theory of rings. And in maths, we also regard many algebraic objects from different point of views. It's a typical approach when we, for example, try to solve some conjectures in algebra or hard problems in algebra by looking at, for example, topological methods or geometrical methods. Let me mention, for example, if we want to find roots of quadratic polynomials, for me, the best way is to use rectangles and squares. So we use genuinely geometric methods to find, for example, roots of a quadratic polynomial. And also, if we, for example, if we are able to associate a topological object to rings, here, then I would call it a motif. A motif is a homotopy type. A motif of an algebraic object is a homotopy type associated to it, which contains more or less, if you know the motif of an object, we understand more or less everything about this object. But instead of having rings and homomorphisms between them, such objects, motifs, also contain much more information, for example, as stated here. Yeah, an application of algebraic KK theory. It recovers, for example, Quillen's K-theory of regular rings or universal bivariant K-theory. So a motif associates to a ring here a genuinely topological type. Yeah, and yeah, I look at rings in terms of the right-hand side. And maybe one day include to MA111 this new look to rings. Why not? Because it is definition entirely uses only rings and homomorphisms. So something very explicit. Okay, and yeah, it's interesting that we associate topological types to algebraic objects, but on the other hand, algebra objects recover classical homotopy types. And this is actually a dual carriageway between algebra and topology. So topologists suggest us to use topology to investigate algebra, and as soon as we are able to compute homotopy types by using algebraic objects only, well, then we can show something to topologists and enhance their view and their constructions by genuinely algebraic objects. And yeah, for example, K-theory, algebraic K-theory space of Quillen is entirely recovered from rings and homomorphisms. Or more generally, it can be regarded as a motif of the integers. Okay, and this is briefly about motifs for rings and transfers. So the groups here, higher KK groups, possess rich transfers in each variable. And this is what typically happens in motivic homotopy theory. The approach of this approach was is due actually to Vladimir Voevodsky, who invented motifs of algebraic varieties and various kinds of transfers in motivic homotopy theory. And it turns out that something similar can be applicable here as well. Okay, and so this is another part of algebraic Kasparov K-theory. And as a summary, the resulting interplay of topology algebra and functional analysis in algebraic KK theory provides a fascinating glimpse of the unity of maths, because it requires several areas of mathematics which at first glance have little to do with each other. Okay, next let me pass to another topic and another activity. Namely, I will briefly mention about motifs and transfers of algebraic varieties. But let me mention first about algebraic topology. Algebraic topology is a largely creation of the second half of 20th century. And one of the most complicated challenges here is to compute vibrant resolutions of spectra. Spectra are basic objects of algebraic topology, and vibrant resolutions, are mostly inaccessible here. In 2001, Voevodsky introduced frame transfers of algebraic varieties. And we read in his notes, I hope that the constructions described here in these notes will lead to a new model of the stable homotopy theory. Stable homotopy theory plays the central role in algebraic topology, which will be more friendly for computations questions. And of course, one expects that it will be non-trivial to show that the new and the old models agree. So Voevodsky envisions a new model of classical stable homotopy theory, which will use the so-called frame transfers of algebraic varieties. Algebraic varieties are basic objects of algebraic topology. They are easy to define. They only use polynomials and the zeros of polynomial functions, and we glue them somehow. And if we have a rich motivic homotopy theory for algebraic varieties after Morel and Voevodsky, and joined with Ivan Panin, we started a research program in 2010 dedicated to the realization of Voevodsky's ideas on the new approach to stable homotopy theory. I should mention that Ivan Panin was a visitor here twice, in 2010 and 2012, each visit for 2 months. Voevodsky kindly shared his unpublished notes with us in 2010, and it was an exciting journey to frame transfers and the realization of his ideas on the new approach to stable homotopy theory. But let me first, as an illustration, let me mention a classical result of Pontryagin in topology. The major object in algebraic topology is the sphere spectrum. The sphere spectrum consists of all possible spheres of all possible dimensions. And homotopy groups of the sphere spectrum can be recovered from the so-called framed cobordisms. And this is an exciting topic of framed manifolds and cobordisms. By the way, the picture on the left illustrates cobordism from M1 to M2. And by the way, the manifold N connecting them is a framed cobordism from M1 to M2, can be regarded as a transfer between M1 and M2. So transfers in practice can look quite exotically, and bodyisms categories play an important role in modern topology, and one of the applications is after Atiyah and Graham-Segal in topological quantum field theories. So this is quite an important area and exciting area. And frame transfers of Voevodsky are actually far relatives of Pontryagin framed cobordisms. And in fact, Pontryagin theorem can be enhanced by constructions based on frame transfers and framed motifs I will mention later. So this topological information and the result of Pontryagin can be enriched and lifted to a richer information. So one of the fascinating applications of the machinery of framed motifs we introduced with Ivan Panin is an explicit resolution of the sphere spectrum. So at first glance, the sphere spectrum, which consists of all spheres of all dimensions, has nothing to do with algebraic varieties, which are entirely defined by polynomial functions and a typical algebraic objects, but it is not the case. It turns out this classical sphere spectrum has an explicit fibrant resolution, and this is one of the main applications of the machinery of framed motifs and framed transfers. It is also worth mentioning that over the field of complex numbers, frame transfers can be essentially identified by means of the implicit function theorem from complex analysis with collection of points in affine spaces together with open neighborhoods and holomorphic functions on them. But a formal definition of a frame transfer looks like this. It's quite abstract. However, if we take X to be a point and the base field is the field of complex numbers, then in fact frame transfer or frame correspondence is essentially the content of the implicit function theorem. So complex analysis lives here as well over the field of complex numbers. For particular varieties, X is point, Y is point, but in general, a frame correspondence is this between two algebraic varieties X and Y. Okay, and the top publication in this direction is this paper, namely framed motifs of algebraic varieties after Voevodsky, published in 2021. But the first preprint archive version appeared in 2014. And by the way, I'm very grateful to Maths Department for sabbatical semester in 2014. It was quite productive. In September 2014, we put the first version of this paper where you can find a sketch of the realization of Voevodsky's ideas on the new approach to stable homotopy theory. This paper also requires further 3 papers, and where are they? This paper, published in Cambridge Journal of Mathematics, Cambridge for Massachusetts, not British Cambridge, Cambridge for Massachusetts, Cambridge Journal of Mathematics, and another paper published joint with Ananevsky in Advances Maths 2021. Preprint version appeared in 2016. And finally, the final step was published in the Transactions of American Math Society in 2021. And this paper was published joint with Ivan Panin and Alexander Neshatov. And I'm very grateful to Maths Department for arranging a visit of Alexander Neshatov. In fact, during this visit, the last step was essentially done here. And yeah, it was a miracle that this final publication completed entirely the where is it? No, this publication was the last step in the whole program on the realization of Vygotsky's ideas. And let me mention one of the theorems from that paper, namely, I can regard the classical sphere spectrum here. What is it? This sphere spectrum can explicitly be computed as the framed motif of the points, evaluated at the points, if you work over the field of complex numbers. So if you give me the field of complex numbers and affine algebraic varieties only, then I will show you how to compute the sphere spectrum, and this spectrum is fibrant in positive degrees. I should mention that only this computation requires all these 4 papers. So we can't avoid any of these papers to prove these results. So this requires all the machinery of framed motifs we introduced and all the computations from all 4 papers. Yeah, as a genuine topological application of the business of framed motifs. Also, I should mention Graham-Segal, and the machinery of framed motifs also allows us to develop motivic counterparts of the infinite loop space. And our results here a kind of homage to Graham-Segal's influential topological theory of gamma spaces. Gamma spaces is a model of infinite loop spaces in topology. And yeah, we also were motivated by Segal's ideas here, and what are motivic counterparts of Graham-Segal's gamma spaces. Another result here, another explicit computation computes the suspension spectrum of any algebraic variety. They are building blocks of stable motivic homotopy theory in terms of twisted framed motifs. And this theorem can also be viewed as a motivic version of the celebrated theorem by Barrett, Preedy, and Quillen in algebraic topology. And I would also mention further recent papers published in 2023. The first paper has been published in Annals of K-Theory in August 2023, joined with Alexander Neshetov, where we extend the constructions and results for framed motifs to cobordism theory, cobordisms, and also give explicit computations of classical cobordism cohomology theories. And another paper was also published in September, where I apply Vygotsky's frame transfers to quite general context. We don't need any geometry, nothing. We only deal with abstract categories where we can produce plenty of transfers and then recover some classical objects. The classical, for example, stable homotopy theory in topology SH is recovered there. Yeah, and I very much hope that the constructions of the latter paper will lead to applications in non-commutative algebraic geometry and classical KK theory of Kasparov, but this is the content of the subsequent papers. And I would like to finish with 3 students of mine, PhD students. I would start with Peter Bonnet, who has just defended his PhD viva, and it is the successful culmination of methods developed in Hassan's thesis and Darren Jones' thesis. And in Peter's thesis, he recovers Vygotsky's triangulated categories of motives, and but it is largely based on the previous PhD thesis of Darren Jones. By the way, his MSc thesis was awarded Swansea University James Callaghan Thesis Prize in 2018. And in turn, Darren's thesis is also largely depends on Hassan's thesis on growth in the categories of enriched functors. And let me stop here, and that's everything I was going to tell about. Thanks.